lots of things vibrate, right? Like, say, a tuning fork, right? So we're going to focus on a type of vibration called simple harmonic oscillation. And simple harmonic oscillation is three things. It's simple, it's harmonic, and it's an oscillation. Oscillation, you've heard before, that's a repetitive back and forth motion. What makes a simple harmonic oscillator simple is that it is a repeating motion that follows Hooke's law. It's something that vibrates one way and then, because of a restoring force, vibrates back the other way, and that force is proportional to how far away it is from its equilibrium position. So examples include a simple pendulum or a mass that is suspended between two springs and are moving back and forth, or a mass bobbing on a spring. These are all examples of simple harmonic oscillators. Some vocabulary that goes along with this would be, say, amplitude. Amplitude is how big your oscillation is, and it's measured from the equilibrium point to the furthest point away. So that is pretty easy to measure for most things. It is a distance and it is a vector, represented typically by a capital A. The units then, if it's a distance, would be meters. The period is the time it takes for one oscillation. That's there and back. Period, of course, is measured in seconds because it is a time, and it's represented by a capital T. Finally, we often talk about the frequency of oscillation. Frequency is the inverse of period. Period is how many seconds for one oscillation. Frequency is how many oscillations in 1 second. So, for example, this tuning fork is 560 oscillations per second. It vibrates very fast. How fast, you might ask? Well, check this out. I've got myself some water. I've got myself my tuning fork. Pretty fast. That's a lot of oscillations per second. Frequency is measured in per seconds, which we call hertz, after Heinrich Hertz, who discovered radio waves. Note that by definition, the frequency is equal to 1 divided by the period, and vice versa. They are reciprocals of one another. In our very first lab at the beginning of the year, we saw that the period of a pendulum depends on only its length, right? Well, it turns out the equation is this. It's the period of a pendulum is equal to 2 pi times the square root of its length divided by the acceleration due to gravity. This is on the AP1 reference tables. For a spring that is oscillating back and forth with a mass on it, that is 2 pi times the square root of the mass divided by the spring constant. So a heavier mass will oscillate slower, and a stronger spring will make it oscillate faster. We will get to the math on that after we finish what the Regents class should know. We'll move into an actual derivation of those equations. Now, often enough in this class, we're going to deal with kind of ideal oscillations, something that as it oscillates, it doesn't get bigger or less big over time. It's just a nice constant amount of oscillation. In real life, that's really hard to do. Most oscillations are damped by friction. And damped means, well, it's like throwing a damp rag on it. It's going to slow down and lose energy to its environment. That tuning fork is a great example. It loses a lot of energy to the air. When I put it in water, it became very damped, and the oscillation died down super fast. On the flip side, if you're, say, shaking a slinky or a rope or something, and you're creating a wave, then that wave is very commonly driven. That means you're continuously adding energy back into it in order to either keep it at the same amplitude or to make its amplitude get bigger and bigger and bigger. A good example of a driven oscillation would be a person on a swing who's being pushed at the right timing to go higher and higher and higher. As just an example of where this could be important is shock absorbers in cars. Your shocks are usually just big springs, and if those springs are underdamped, then what's going to happen is when you hit a bump, your car is going to go and it's going to keep going for a little while, and it might get you a little queasy or seasick. If it is overdamped, then it's almost like you don't have the shocks there at all. It hits, and then you just smash down, and that's not very comfortable at all either. You can have something that is critically damped where it's going to very smoothly go from a big oscillation back down to zero. And in general, for comfort in cars, we aim for a very slight underdamping. We aim for something where you hit a bump and then you go up and down a little bit and then it settles in place pretty quickly. It is an oscillation, but it's a pretty quickly damped one. In very fancy cars, sometimes they use something called a magnetorheological fluid. A magnetorheological fluid turns into a solid in the presence of a magnetic field, and the stronger the field, the more solid it becomes. So instead of using a spring shock, you actually have a piston that's floating in this fluid, and based on how hard it's moving, the computer will detect that speed and change the stiffness of the fluid. That's like changing the spring constant of a spring with an electromagnet as it bounces in order to get exactly the damping you want. It's pretty fancy, and you typically only see it on some pretty expensive cars. All of these types of oscillations have something in common. If you were to look at just the shadow of a mass bobbing on a spring, you'd see it going up and down and up and down and up and down. It'd be going fastest in the middle, it would slow down and stop, and then it would speed back up again, and it would just repeat back and forth. If you were to look at the shadow of an object being spun in a vertical circle, you would see that shadow doing the exact same thing, moving up and down. The same thing is true if you looked at the shadow of a pendulum. A pendulum is doing this, right? Well, if you turn it sideways and look at it, you see something that is undergoing the exact same motion. And all of this is basically a wave. And waves and simple harmonic motion have a lot in common. And all of that has a lot in common with an object going in a circle. And so you've talked about the unit circle in math with sine and cosine. It shouldn't surprise you too much that the math of a simple harmonic oscillator is identical to the math of a wave with sines and cosines and things. So this is the point on this video where Regents can bail out, and we're going to dig deeper into the math for the AP1 class. Let's do it.
You can time this with a stopwatch if you want to. When we take a mass and we let it oscillate back and forth between a pair of springs, it does so with a certain period. If we quadruple that mass, the period doubles. And if we octuple it, it goes up by the square root of 8 to about 2.82 times the original period. So let's take a look at some of that math. Starting with Hooke's law, we can say F equals Kx, which equals ma. That gives us A equals minus Kx over m. Let's apply that to conservation of energy. The initial energy equals the final energy. That means that the potential energy when it's stretched a maximum amount is equal to the kinetic energy plus the energy for however far it's stretched where it's at. Plug in your equations, including your amplitude for x, and then cancel your 1/2 and solve for v. We get this equation here, which tells us the velocity is at a maximum when x equals 0, and that when x equals a, velocity is 0. Exactly what we'd expect. But what about period? Well, velocity is distance over time, which is circumference over time, which is 2 pi a over time. So period is 2 pi a over v naught. Well, looking back at conservation of energy, we get 1/2 ka squared equals 1/2 m v naught squared, and the ratio a over v naught gives us the square root of m over k. Substitute that in, and we get the equation for the period of a mass on a spring. And of course, frequency is just 1 over that period. The math for the period of a simple pendulum is extremely similar, and you can find it in your book, so we're not going to go over it here. Deriving the position function of a simple harmonic oscillator is as simple as combining trig with some of the equations we already know from circular motion. Position is amplitude times cosine theta, and theta is omega t. That makes x equal a cosine omega t. Well, what is omega but angular speed? It's change in angle over time. That's 2 pi radians per period, or 2 pi times frequency. Substituting that in, and we get x equals a cosine 2 pi ft. From here, it takes a lot of really messy algebra or some very, very simple calculus to get the equations for velocity and acceleration. And to be honest, it's easier to just leave this until you know how to do derivatives in calculus. For this class, you really only need to know the position function anyway.
So this next part, I apologize, I didn't have a great place in any of the other videos to put it. This equation should look familiar. This you've seen in math class for describing a sine function or a cosine function over time. And all of these parts are very analogous to an equation that looks similar in physics, and that is this. These two equations are the same thing. They just have slightly different nomenclature. In math class, you used A as your maximum amplitude of oscillation. Well, turns out the same thing is true in physics. In math class, you use capital B as the angular velocity in radians per second, but in physics, for angular velocity, we use the Greek letter omega. In math, the period is 2 pi divided by b, which should make good sense given the relationship between period and frequency. That's 2 pi over omega is the period in physics class. In math, you called h the horizontal shift. In physics, we use phi the phase shift. It's the same thing, only in math class, you always use a negative, and in physics, we could use a positive or a negative, depending on what we want to do. We very commonly, if that phase shift is 90 degrees or a multiple of 90 degrees, instead of using that, we will simply switch sine to cosine, or vice versa. And finally, in math class, you have this plus k. That's your vertical shift for moving it up and down. In physics class, we pretty much always just pick our reference frame to be wherever the equilibrium position of the medium is. And so that never comes up. So we just pretty much always make that 0 by good choice of our reference frame. So there you go. That's the basics of simple harmonic motion and how it relates to waves. In our next video, we're going to get into some types of waves and what they look like and some things like that. So we'll see you there.